Alrighty, good evening guys. Tonight we are going to be talking about limiting reactants and percent yield, like I said in class. So, let's just take another quick look at stoichiometry, because if you don't understand stoichiometry, then we're not going to be able to do limiting reactants. So stoichiometry is the method in chemistry that we use to be able to go from some amount of one substance to some amount of another substance. It's how we relate things to each other. It's how we take information about one thing and apply it to gaining information about something else. In order to do this, we must have the balanced reaction that is occurring and a balanced chemical equation to go with it. So we need to know what reaction is going on, and we must absolutely have to have a balanced chemical equation. From this, we can get the mole-to-mole ratio, which will allow us to convert from one substance to another. So these are key things that you have to have in order to be able to do anything in stoichiometry. So what I'm talking about here, like I said in class, it's an amount of X going to moles of X, which goes to moles of Y, which yields some amount of Y. Now, if we're going from amount of X to mole of X, if we're talking about grams, we're going to use the molar mass. But if we're going from moles of X to moles of Y, we're going to use the mole-to-mole ratio. And then going from moles of Y to amount of Y, if the amount is grams, we're going to again use molar mass. Now, this one here, from the amount to moles, if we're dealing with grams, it's molar mass. If we're dealing with volume, you're going to use 22.4 liters per mole, and then if we're dealing with particles, you're going to be using Avogadro's number. So this part right here and this part right here is mostly dealing with the mole map. So let's talk about limiting reactants. In the reactions we've been looking at so far, information has only been given about one of the reactants, indicating that the other is in excess, meaning that there's more than enough of it to go around. In reality, though, we often need to know the amount of all reactants, and this can help to determine the limiting reactant, or the reactant that determines the amount of product we can form. So if a reactant is in excess, we have more than enough of it. If it is the limiting reactant, we only have enough to make as much product as we can, and then we run out of that reactant and we can't make any more product. Does that make sense? So the excess reactant we're going to have left over at the end. The limiting reactant, we will have no leftover at the end, and it is the amount that determines the amount of product we can form. That's really key. So in order to solve for the limiting reactant, we're going to follow the following, I think it's 5 steps. So the first one, we're going to write the balanced chemical equation. After that, we're going to calculate the molar masses of all compounds involved. From each of the starting materials, we will determine the amount of the desired product that could be formed. Now, we can either do moles or we can do grams when we're talking about amount. It doesn't really matter. Going to moles is the easiest because then it's just one step less. And then you compare the two product amounts. The lower amount is the amount that will form, and the reagent that this is from is the limiting reagent. The other reactant is the reagent in excess. Okay, so you're probably going to want to write these down or read them over again and again to figure it out. But those are the steps. When you're done with that, we're going to do an example. So methanol undergoes a combustion reaction. How much CO2 is formed when 130 grams of methanol reacts with 150 grams of oxygen? So the first step is to write a balanced equation. So I'd like you guys to pause and write the balanced equation for methanol combusting. So you should have found that you needed to have methanol, CH3OH, plus O2, yielding carbon dioxide and water. Now, next we need to balance the reactants for the equation. Whew, sorry guys. So if we look at the left-hand side of the equation, we can see that we have 4 hydrogens, and on the right-hand side we only have 2. So we're going to need to fix that. So now I have 4 hydrogens on both sides. Now if I look at my oxygens, I have 3 oxygens on each side. That is balanced. And I just realized that I totally overbalanced this reaction. Because I then put 2 more and 4 and 3. Oh wait, how did that work? why aren't we balanced here? Help me figure it out, guys. Oh, okay. We aren't balanced. Sorry, guys. If we look here, and I'll show you why we aren't balanced here in a second. If we look here, we have 1 oxygen plus 2 oxygens. We have 3 oxygens. And over here, we have 2 oxygens plus this oxygen times 2, so 4 oxygens. All right? So this is unbalanced. So, okay. I didn't do it wrong. Okay. So now that we know that, we are going to need to balance the number of oxygens. So usually when we do this, we're going to start with these carbon dioxide ones. So we're going to start with the oxygen over here, the oxygen that was the odd man out. So now I have 2 oxygens plus 2 oxygens is 4 oxygens, which I have 2 oxygens and 2 oxygens, which is 4 oxygens. But now I have 2 carbons, so I'm going to need to fix that. So now I put 2 carbons out here. And now I've got another problem. I had 2 times 3 is 6, plus 2 is 8 hydrogens over here, and I only have 4, so I'm going to need to fix that. So I can fix that by putting a 4 in front of here and making that 8, but now I've screwed up the oxygens again, so let's count. I have 2 times 2 is 4 oxygens from this side, plus 4 oxygens is a total of 8 oxygens, and over here I only have 2 oxygens, so if I put a 3 in front of here, this becomes 6 oxygens, plus 2 is 8 oxygens. Okay? Sorry, I know that was kind of spazzy, but bear with me. Hopefully you were able to more easily balance that than I just did. Now, the second step is to calculate the molecular weight or the molar mass of all the substances involved. And so here we're looking at how much CO2 is formed. So we're going to be needing the molar mass of methanol, oxygen, and CO2. So the molecular weight of methanol is as follows: a carbon atom plus 4 hydrogen atoms plus 1 oxygen atom is 32.041 grams per mole. For O2, it's just 2 oxygen atoms, so 31.998 grams per mole. And CO2 is a carbon plus 2 oxygens, which is 44.08 grams per mole. The next step is to determine the amount of product formed from each of the reactants. So we're going to start with methanol. So if I have 130 grams of methanol, and then it's just stoichiometry again, guys. So 130 grams of methanol, multiply it by its formula weight to get to moles, multiply that by the mole-to-mole ratio. For every 2 moles of methanol, I create 2 moles of carbon dioxide. And that gives me 4.057 moles of carbon dioxide. Now if I do that for oxygen, I start out with 150 grams of oxygen, multiply that by the molecular weight of oxygen, O2 gas, and then multiply that again by the mole-to-mole ratio. For every 3 moles of oxygen, we create 2 moles of carbon dioxide, and I make 3.158 moles of carbon dioxide. So here we can see that I make less carbon dioxide with the amount of oxygen that I have. So oxygen is going to be our limiting reagent. And so I'm going to take the amount that I have the least moles of for carbon dioxide, and I'm going to try and find out actually how much is produced. So I start with the smallest number of moles of carbon dioxide, multiply it by its molecular weight to get 139.0 grams of carbon dioxide. So that's the most carbon dioxide I can make. Now you'll notice here that it was a 2 to 3. There was 2 moles of methanol and 3 moles of oxygen, and yet oxygen was still the limiting reagent. These stoichiometric numbers, the coefficients out here, don't always indicate the limiting reagent. And oxygen, I actually had more of it. Not only did I have more moles of it, but I had more mass of it, and yet it was still the limiting reagent. So don't jump to that conclusion each time. It's not always the one with the fewest number of grams. It's not always the one with the most number of grams that's the limiting reagent. It just kind of depends on the specific reaction you're dealing with. So the limiting reagent was oxygen, and therefore 139.0 grams of carbon dioxide is going to be formed. Now we can go further with this, but I'm going to do that with you guys tomorrow in class. So just now I want you to understand this. Now from this, since chemistry doesn't always happen how it should in a laboratory, we're often not able to produce as much product as would be indicated by the chemical reaction. We therefore like to calculate the percent of product that was actually formed in order to determine the effectiveness of the experiment. And we do that by using an equation that says percent yield is equal to actual yield divided by theoretical yield times 100. So the actual yield here is how much you actually make divided by what you theoretically should be able to make based on the chemical equation, times by 100%. So let's take that example. So if in the reaction to produce carbon dioxide, you only in fact produce 102.3 grams of carbon dioxide, what is the percent yield of this reaction? So we're going to do the actual amount, 102.3 grams of carbon dioxide, divided by the theoretical amount, which was 139.0 grams of carbon dioxide. Multiply that by 100. So 139, again, is the mass of carbon dioxide that we determined would be formed in that reaction from our previous example. So if I divide my actual amount that we made divided by the theoretical amount that we should have made, multiply it by 100, I can see that my reaction was 73.60% yield. So it was pretty effective. A 73.60% yield is actually not that bad in chemistry. Okay, so tomorrow I want you to come geared up and ready to go with practicing limiting reactants. We are also going to be doing a very fun activity on Monday that you'll need to do a little bit of work for over the weekend. So get ready for that, and I will see you tomorrow.